Hi everyone, welcome to this webinar. The webinar title is Unlocking Precision with the New Block Model in Slide 3 and Slide 2. I will be hosting this webinar today. My name is Sina Javankhoshdel. I'm the Geomechanics Product Manager at Rock Science. I'm the Product Manager of Slide 2 and Slide 3 software. And in this webinar, I'm going to talk about the new feature released in these two software recently. We are Rock Science. We are the world leader of geotechnical, mining, and civil software packages around the world. We have over 25 years of experience, and we have grown to a team of more than 80 people in our head office in Toronto, and we have over 10,000 customers around the world. We have 19 software packages, as you can see them here. These software packages, they are for different applications. And today I'm going to talk about two of them, a Slide 2 and a Slide 3 software, which are our 2D and 3D limit equilibrium software packages. Before I get to the presentation, I just wanted to show you, this is the ecosystem of Rock Science programs. As you can see, each program is integrated with different other programs. For example, Slide 2 and Slide 3, they are integrated with each other, as you will see in this presentation. And also, they are integrated with other software packages as well, which is make it a unique feature to all of our programs. You can run the same model with different methods or use different software to provide inputs for other programs at Rock Science ecosystem. So today I'm going to talk about two of our major software packages, Slide 2 and Slide 3 software. The feature in these two software, which is called block model. Slide 3 used to have the block model feature. We upgraded this feature and we are presenting it here. And I'm going to show you the differences between the new feature and the old feature. And Slide 2 didn't have this feature before. So we recently added the feature to Slide 2, and I'm going to talk about that one as well. I hope you enjoyed the webinar. Please feel free to ask questions during my presentation. If you have any question, any concern, please type it down in the question section, and I will answer the questions at the end. So, before going to the block model section, let's start about the general 3D geotechnical modeling. And we get to the block model after this. So, when you do the 3D modeling in general, you most often require a couple of geometries imported to your model. They include geology, which basically there are volumes of different lithologies or the contact surfaces between the adjoining lithological units and faults. They include excavation geometries and topography, and design geometries coming from mine planning and CAD teams, and groundwater tables from the hydrogeology. So not necessarily you need all of them for your model, but most of the time you need a couple of them. And this is an example of an open pit mine. As you can see here, we have different lithologies. Basically, you can see different colors, which are different material regions. You can see your pit shell, which is a slope geometry element. And also further away, you can see the topography. So in one picture like this, you can see all these aspects of 3D modeling. So what are the limitations of 3D geometry modeling? First of all, 3D geometry shapes, no matter how complicated they are built from triangles, or called faces, with edges and vertices. And due to the limitation of 3D geometry collection devices and triangulation algorithms, surfaces and volumes generated by these several different software packages out there are often corrupted by geometric errors and defects, which are challenging to fix. So what do we do? First of all, just keep in mind, in rock science 3D software packages, we have tools, very advanced tools to fix these defects. But let's talk about the defects first. So there are different types of defects coming when you import the geometry into the software, similar to near degenerated triangles, holes, non-manifold geometries, near folded triangles, self-intersecting triangles, inconsistent triangles, normals, and tiny gap between neighbor volumes. So these geometric errors are often not an issue in the original 3D software. So basically in the original 3D software, everything looks fine. But when you want to do a 3D geotechnical stability modeling, situation can be fatal. And as a result of geometry imperfections, geometry building of 3D models can consume up to 90% of your modeling time. So 3D modeling, 90% of the time can go to the geometry creation. And it can take 40 to 80 hours for expert modelers just to create the geometry. And simplification and correction of geology volumes can consume up to 80% of that 40 to 80 hours. You can see how important it is to model the geology. And these are different types of defects. Like, as I said, they are all related to triangles, the shape of the triangles, the connection between the triangles, the space between them, intersection of them. So all cause issues. And why do we need to clean them up? It's very important to know the reason. We are talking in general, limit equilibrium, finite element. For example, elimination of errors and inconsistencies, mesh quality in the finite element software, convergence in the finite element software. Even in the limit equilibrium, you might have convergence issues because of geometry issues. Reduction in computational cost, accurate representation of geological features, and compatibility with analysis software, and better visualization and interpretation. So you can see how important it is to have a clean geometry. This is an example of complex geometry that we have a tutorial in the Slide3 software. We added recently 3D model cleanup and creation tutorial. That is step by step we showed you how you can use a Slide3 to clean up the geometry. But in general, there are three potential solutions. Geometry cleanup tools, which is available in Slide3 and RS3. So you can clean them up and build your geometry. Use boreholes to create geology. I'll show you an example. And finally, use block models for mining geology. So these are three different ways of creating your geology, which is the most complex part of this geometry creation. This is an image how we have the geometry cleanup tools, repair tools in a slide that you can see the defects here, and the software is going to repair them for you. Recently, we had a webinar called Masterclass on 3D Model Creation with the Slide3 and the RS3. In this webinar, we explained step by step how to use the Slide3 and RS3 to clean up your geometry and to create a valid model. If you have a borehole, and we have a couple of boreholes, and you have your raw geometry, the software can automatically use these boreholes to create the geology for you. So this is another way of creating geology in your model. And finally, the block model. So block model is another way of creating geology in your complex model. And this is an example that you have a block model, you have a raw geometry, and we use this block model to create a geological regions. So let's see what block model is. Majority of mines, they build 3D block models for their geology. So it's part of the process of making geology regions. The block model is created using either geostatistics or the geological data gathered through drilling of the prospective ore zone. Block model is essentially a set of specifically sized blocks in the shape of mineralized ore body. These blocks, they have the same shape and same size, but their characteristics might be different. And each block has a measurement of values such as ore grade, lithological units, geotechnical parameters, different types of parameters. This is an example, a screenshot of a CSV file that we had for a block model. You can see that each block has its own ID, its own coordinates, dimensions, and material names. They have properties. So a block model file comes with all sorts of information that I'm going to show you how to use them in the software. Already built-in models could be used to develop geological geometry and material properties of 3D geotechnical models for stability. What are the advantages of these block models? First of all, that 40 hours time to create the geology can go down to 40 minutes. It's going to be way easier. And also, the ability to significantly increase to usability of 3D modeling in mining. Because a lot of mining projects, a lot of models, if you make it easier for the mining industry to make the models, the application of the 3D stability is going to increase, because now it's easy to create the model and everybody can make a 3D model using their block model. So that's the main advantage of this block model feature. So we had a block model version 1 in a slide 3, which we released in 2022. And it had a couple of features. A slide 3 basically allowed you to import your block model. It verified the block file and created the material regions that were available in your block model. Users could import the material properties using CSV file and assign them to materials of the block model. And the material block model also, if you didn't have any pit shell or anything, could be used to create your external geometry. And at the end, if you had your pit shell or you had any faults or any surfaces, you could cut your block model external using any volumes or surfaces. What were the limitations? Material parameters could not be defined at the block level. So it was just a regions of material. We didn't have any 2D section visualizations, and 2D sections could not be analyzed in a slide 2. Also, there was another limitation that the block model could not be projected on your pit shell, on your external volume. So that's why now we have a block model version 2, which we released a couple of weeks ago in a slide 3 and slide 2. And we have new features. First of all, new user interface has been designed for the block model. Now users can assign different material parameters to different blocks. So properties can be defined at the block level. This is the biggest improvement to the block model feature. Also, the users can import pit shell and block model will be projected onto the external geometry, in addition to create an external using block model. So now you have two options. If you have a pit shell, you can use that. If you don't, you can create your external using block model. Performance has been improved. And also, this is another big advantage here, big improvement. Users can readily generate 2D cross-sections from block model and export them to slide 2 and do the 2D limit equilibrium analysis. And when you are creating these 2D sections, 2D cross-sections, you can visualize your block model on your 2D section. So you can see even at block level cases on your 2D section. So let's see what are the new stuff that we have. This is the new user flow. So the first step, we're going to ask you what are the block level parameters that you have. So these are the block level parameters. You can pick. Then if you don't select at the block level parameters. You have to assign X, Y, Z, and material. You have to assign a column to them. But if you have the block level material, you have to assign some columns to these parameters as well. Then we have the estimator. Estimator is basically validates that if from the data that you provided, we can make a valid block model geometry model. And you can see that, for example, in this case, we have 6 million blocks. All 6 million blocks conform to the parameters that users provided to the software. Then, if you have the properties defined on the material properties section, we're going to map the block model property to those. If you don't have the properties that they are in the block model on your list, the software is going to create those for you. So there are two ways. Either you define the properties here and we map the block model properties to those, or we generate those for you. And at the end, we project the block model onto your external geometry. You can see that these regions are projected regions from the block. And then if you want to take the 2D section to slide 2, you can create a 2D section here. And the software is going to show you the block model here. So this is a new improvement to our block model feature. So you can see the regions that you have block model on the 2D section creator. And finally, you take the 2D section to slide 2 software and you can do the 2D limit equilibrium software. This part is very important because we know a lot of our users, they used to create these block models in a slide 2 manually. Now they can bring it to slide 3 and take as many 2D sections that they want and take it to slide 2 and do the 2D limit equilibrium analysis, which is very important. So let's go to our first example. I'll try to start from simple examples to cover the features that we used to have and to go to more complicated examples. This is a slide 3, as you know, and to create a block model, basically, we need to go to the material dialog. But before that, I want to show you this model because this model, we created it using volumes and surfaces. So this is the model. So these are the volumes that they were created. We imported the volume, we imported the surfaces, we created different material regions. So we have all these material parameters. Now I have a file with the block model of the same model, and I want to create the same model using block model. So we go to the materials, define material, and here for material 1, I'm going to change it to block model. So if you want to create your block model, it's here. Click on it. Here, you have to import your block model from a CSV file, from text file. So you can just click here. And for the first example, I have this text file. If I open this text file quickly and bring it up here, you can see that in the text file, we have the number of blocks, which is 169,000. It's a very coarse version of that model. You have X, Y, Z, and material. So you can see all the information here. So I select this one, hit open. A new dialog will pop up. So this is the block-based parameters that you need to select, which is not in this case. So I don't select anything. I click on next. Here, you need to assign different columns to X, Y, Z material. And also you need to tell the software at what row we're going to start our block data. So you can see it's row 8. So I'm going to type 8 here. And you can see that now you have just X, Y, Z and the material name. These are the material names that I showed you in the original model. So if you click on next, now you need to estimate and see if we can create a valid block model or not. So click on estimate, it's checked, and you can see that block size is here and number of blocks in each row. So if you're not happy with this estimation, you can click on edit, put your own data here and validate the new block model that you are creating. And if it's validated, it's fine. So we click on next. Since I started a fresh Slide3 file, the materials that I had, they were not on the list. So these ones are being generated from the block model file. So if I click on finish, you can see that the materials, they are here. Now, any material that we generate in the block model file that we have, the example file that we have, there are just general subprod, and the parameters are the default parameters of the software. So if you want to define your own parameters, you can define them here. So if I hit OK, the block model is created. Now, I have two options. Either I bring my pitch shell and create the external geometry and assign the block model to it, or I can create block model from external, which used to be available in a Slide3. So we'll do that. So we go to geometry, block model, create external from block model. Once I click on it, what the software is doing is it's gonna generate my external boundary, and also it's gonna generate the geology inside my model. So it's gonna generate everything together. And then once this is generated, then you can play with the geometry, cut it, or define your pitch shell, or whatever you want. So if I go back to this, so you can see that two things are being generated here. Block model function. If I hide it, my external is generated using block model as well. So if I reduce the transparency here, so you can see this is my open pit and the material regions coming from the block model, equivalent to the model that I showed you that was created using volumes and surfaces. For this model, because the big question here, how they are compatible, how the results are compatible between the model generated using volumes and the model generated using block models. So for this one, I can run it with the spline. I encourage you to watch the webinar that I had about the search methods, intelligent search. But for this one, I'm going to run it with the classic search, spline, and particle swarm optimization, which I did before, and I can just show you the results. So if you go to the results tab, this is the model that was created using the volumes and surfaces. And the factor of safety is 1.5 using a Yambu method. And if I show you the model that was created using the block model, this model, let me hide the block as well. And turn on this one that you show that this is the block model. Factor of safety is 1.52. And as I mentioned, the block model that we had for this model was a very coarse version of the original model. But even that, the results are very close and they are equivalent. One more thing that I wanted to show you on this model is, as I mentioned, you can add any geometry and you can cut your block model using surfaces and volumes. So I'm just going to add a plane that cuts my external and hit OK. And just imagine I want to cut my external block model with this surface. So I go to geometry, 3D Boolean, divide all geometry, and I hit OK. So the software is gonna use this surface to cut my external block model, and it's gonna cut it in half, and the rest of the surface will disappear. So we'll see what's gonna happen. So the process is called divide all geometry. If you are a Slide2 or RS3 user, you're familiar with this concept. So basically, you can see we have volume external 1 and external 2. And if I hide the external 2, you can see that you can see the block which is under the external 1. So this is my block model. So recently, block model is the second big feature that we released since the beginning of this year. And the first one was called Intelligent Search. Intelligent Search is an AI search method and is designed for better and more comprehensive search of big models. And you can see how these particles, they move around and they find the lowest factor of safety. They are focused on different regions to find the local factor of safety. And you can see the safety map here that shows the critical regions, which are the red regions, and safe regions. So this is a game changer, basically, in terms of searching for the critical slip surface for 3D models. The reason that I brought it here was a block model feature is mostly for big mining open pits. And if you create a model using block model, we do recommend that you use intelligent search because intelligent search is designed for those kind of models and to give you the most accurate results. So I want to combine these two new features of a Slide3 and create a model and run it and show you the results. Just keep in mind, I had a webinar, as I mentioned, about the intelligent search a while back. And I explained from the basics of 2D limit equilibrium search to the advanced AI-based intelligent search, different search methods. And if you have any questions regarding the search, you can watch this webinar. So let's go to our second example. Basically, in this example, we want to look at the differences again between the results of the block model and a model created using solids. And this model is the big model. It's more than 5 kilometers by 5 kilometers model. And we want to know for this one, how block model can represent the results and how much is comparable to the results of the model created using solids. So for this one, I have an initial file. The reason that I have initial file is because I defined four different materials with different properties of cohesion and friction angle, defined using Moore-Coulomb failure criteria. And I want to show you how the block model properties will map to this material. So for this one, I'll go to material 5, and I'm going to change it to block model. Then I'll import this one, which is a block model function. I want to show you this one as well, because in this one, you can see that we have material 3, we have material 4, and material 1. So in our block model, we have the same names as the names that they are defined here. So I'm going to open it. Again, no properties at the block level for now. This one starts at the row 8. And you can see again material 3, material 4, and material 1. We click on next. We estimate the block model. For this model, we have 1,300,000 blocks. So it's quite larger than the other one. We click on next. You can see that the dialog that you saw in the previous example did not come up because all the properties, material properties, names actually that I had in the block model file, they are here. So you just need to click on finish and nothing is being added after material 5 because the software mapped and checked if you have the names here. So material 4, material 3, and material 1, they are defined here. I hit OK. For this example, what I'll do, I'm going to import a geometry. I'm not going to create external from block model. So what I'll do, I'll go to geometry, import, export, import geometry, and I have my OpenPit as a volume, like this. I'm going to import this volume. This is my volume. The block model function is not generated yet. I have to, first of all, set this one as external. So now there is a lock in front of it. Now I have the external. Then to make the block model function and to project the block model on my external, I need to change this material to material 5, which was the block model material. So once I click on it, you can see that the block model function will be generated. And at the same time, it will be projected on my external. So you can see if I reduce the transparency here. So this is the projected block model. How do we know that? If you click on this external, you can always turn on and off blocks visibility. So if I turn it off, you can see the raw geometry. And if I turn it back on, you can see the projected block model. So that's how we project the block model onto our external. Then we go, I want to run this one using intelligent search because, as I said, it is a big model. So we go to surfaces, slip surface options, change the classic search to intelligent search, and the default is moderate option. So if you hit OK, you can compute this model. So I computed this one in advance as well. So I'm going to bring it up. So I have two versions of it. Again, this version, the first version is just volumes created using like surfaces and volumes. And intelligent search gives you 3 slip surfaces at 3 different locations. So if I turn on the safety map, you can see that these are different regions of critical regions of the model. So that's the solid one. Now I ran the block model version for this model as well. So for this one, if I turn off the block model, and if I turn on the geometry, that you see that it's on the projected geometry. So let me hide this first. I show you that this is the block model. This is the block model. And now we can look at the results on top of this. So basically, we have 3 different factors of safeties for this one as well. So if you want to compare them side by side, we go to the window option, tile vertically, and I can show you side by side that exactly the same regions and very close numbers in terms of factor of safety values. So these 2 models, they are huge models. I ran them using the intelligent search, and you can see that they are almost equivalent, the block model version and the solid version. Next, we have another example, and this is going to be our last example of this webinar. So basically, we have open pit again. And this one, properties are at the block level. And also, I want to show you what happens in the Slide2 software. How do we do block model in a Slide2? So let's go to our presentation. And we have an initial file here. In our initial file, we have 4 different materials defined. So in this example, there are materials that they are already defined, and there are materials that they are not defined. So we have 2 different types, combination of the previous 2 examples. And we have a material named block model. So for this one, what I'll do, I'm going to change it to block model. I'm going to import the block model. For this example, if you see my folder, I have 2 files. One is a block model file, which just defines the block models and the material regions. And I have one file that defines the material properties. So I'm going to show you another feature in the software that you can import the material properties separate from the block model. So first, let's open the block model. For this example, we have deep and dip direction as block level properties and GSI as well. We click on next. As I mentioned, when you have a case like that, you have to assign columns to these 3 as well. But here, since I'm going to import the properties using a separate file, we don't assign anything to them. And just for the first row, I'm going to start from the second row. I'm going to skip the first row and click on next. This model is a very larger model compared to the previous example. So this is the model with 6,800,000 blocks. So we are estimating it. You can see that it's fine. We click on next. So this is gonna import these material material regions, and it says, okay, some of these materials, they are defined in your block model file, but they are not on the list. So when I click on finish, overburden is in my block model, but you can see it's not generated here because it's already exists, and the other ones, they are being created. So let's look at this rhyolite material, and for this one, I want to change it to generalized isotropic material. The generalized isotropic material, you need to define a new function to define your base material, define your bedding material, deep and dip direction, A and B. But we know that this is a new feature here, that we have some properties at the block level, and we define deep and dip direction at block levels. So if I click on select, you can see deep and dip direction, they are at block level. Once you select those, you can see that you have minimum, maximum, and the mean value of the parameter. So for any block level parameter, we provide you with mean, max, and the average, the mean value. You need to define your base material, you define your bedding material or joint, and A and B. Let's put 5 and 10 for A and B. When you hit OK, this material is being generated. We had another parameter at the block level, which is GSI. So for the mineralization material, you can see that here, because at the beginning, we mentioned that GSI is going to be at the block level material, we just have a checkbox in front of it. So if we define others, these checkboxes, they were active for others as well. So I'm going to just click on this one, which is at block level. Again, mean, max, and average value is there. So everything is set. My materials, they are set. And something that we have not defined yet is the properties. So for the properties, we go to click on this plus button and go to import materials. Click on it. I want to import unit weight as well. and I'm going to change it to General Supra. When I hit OK, it's going to ask for a file again. I'm going to pick this material properties file, click on open, and it's going to open this material property dialog. So for this one, I will put 2. Then it's going to be 1, 3, 4, 6, 5, and 2. So you can see that this is unit weight DMIGSI-UCS. And this is the name of the material. When I hit OK, it's going to ask me for what material you're going to add this. I'm going to select all of them and hit OK. For this model, I created in advance as well. I'm going to bring it up here. And we look at the results. So the model is created, the geometry is created. If you want to look at the block model, this is the block model. The software is going to show you the block model, and the block model is created. So once you have the 3D model and 3D block model and your results, then you can create a 2D section on top of your 3D model and look at the results of the 2D section. So if we go to a section creator that we have, this one, you can see that in this model, we have 3 different regions, 3 different results, 3 different critical regions. And you can create a section. We have a new feature in a slide in the interpret, create 2D sections through global minimums, that the software automatically create 2D sections for you. So if I click on this one, if you have 3, if you have 4, if you have 10 critical regions, the software is gonna create 10 2D sections in your model. They all go through your minimums. So you can see that we had 3 minimums. They all go through the minimum. Now, an important thing here is the block model. So in the 2D section creator, you can see that these block models are generated. And these are corresponding to the critical slip surface. So I had 3 minimums, and I can create 3 sections. Okay, so if I click on OK, these 3 sections, they are being generated, and we can take them to a slide. You have 2 options. Either run the Slide2 engine on top of a Slide3 and look at the results, or you can go to the Slide2 modeler and look at the results of the 2D analysis. So I have 3 sections here. So I can go to compute export and pick the section that I want. I only pick the minimum, the first minimum, which is the global minimum slip surface. And I click on open. It's going to open the Slide2 software for me. So, and this Slide2 version, is this Slide2 section, is gonna have the block model in it. So just keep in mind, when you want to have block model in a Slide2, it must come from a Slide3. So a Slide2 independently does not have the block model. You cannot define it independently in a Slide2. It's a feature that it must come from a Slide3. Something like that. So first of all, we have so many vertices, and we recommend all the time to simplify these vertices. So we have an option called simplify boundary. I'll go and click, and there is an option called distance from the original boundary. So I click on apply, and it simplified these vertices. For this model, we just need to check if it's right to left or left to right. It's right to left, which is correct. Now let's look at the block model data for this model. So if you go to properties, define material, you saw that for mineralizations we checked, and also for rhyolite, we had this as well. So deep and deep direction. 3D details, so it says we have the apparent angle. These are coming from slide 3, and we have deep and deep direction at block level. And block data, you can see that deep and deep direction are selected. You can uncheck this if you want and run it, but it's selected as a default because it's coming from slide 3. That's one thing, and for the mineralization as well, so GSI is here. Also, we have a feature in slide 2 called Property Viewer that you can look at the parameters that you have at the block level using Property Viewer. So we go to deep and deep direction, which we define them at block level, and they are defined in these 3 different regions. And if you zoom in, you can see that it shows you the orientation of these arrows show the orientation of the deep and deep direction in your slide 2 model. And also we had GSI at the block level. I'm going to change this contour option to custom range of 35 to 75. Click on apply, and you can see here in these regions your GSI is at the block level, so you can easily see the block level data using the property viewer as well. Then we can compute it. So the options are particle swarm and with single case. So I'm going to compute this one quickly just to compare the results with the results of the 3D model. So it's just for the Bishop method. We're going to run it in the 3D model. We had the Bishop as well. Our lower factor of safety, minimum factor of safety was 2.26. And the 2D one is done. So once the 2D results, they're done, you can bring them to the Slide 3 software and look at the results, compare the results. Factor of safety is 1.9. It's going to be done soon. It's not going to go lower than 1.9. So 1.9 compared to 2.26. It's within around 15% of the results of the 3D model. So 3D model is larger for 15%. Which is reasonable. And when just keep in mind, when you have anisotropy in your model, the difference might be more than 10-15%, which is a typical range that we mention to our users. So this is the critical slip surface coming from slide 2, and I just need to go here and refresh the results. So it's going to refresh the results of a slide 2 section on top of my slide 3 model. And then what you can do is you can compare the results of the critical slip surface of your 2D model with the critical slip surface of the 3D model. Just keep in mind here, in a slide 2, we have property viewer for our interpreter as well. So if you have any parameter at the block level, you can look at it here as well. If I apply this, you can see that these are the regions with the changeable GSI, and this is the factor of safety, and it is in the region with the GSI of 35. So if I go back to my model, you can see that this is the critical slip surface. You can see critical slip surface of 2D and 3D matches. They match, and you can see just the values are different, which is the nature of the 2D and 3D analysis.